We've seen that we can find the sum of a series that converges if we can use the definition of convergence. In particular, we've seen that this works with telescoping sums and geometric sums. But we haven't encountered any other series yet where we can actually find the sum once we know it converges. And in particular, the tests of convergence or divergence that we've encountered have not given us the ability to do so. What I want to talk about in this video is the idea that the next best thing would be to approximate the sum of a converging series and hopefully be able to bound the resulting error. So to give this a general setup, consider the series, or I should say the converging series, that we'll write as the sum of a sub k, but I'm going to specifically call the sum S. So this series converges and the sum of this series is capital S. So we want to assume here that S is unknown. So this is going to be an instance where it's not telescoping, it's not geometric. We don't have knowledge of the exact sum of the series. What we can do is we can use the nth partial sum of the series. And remember that we often use our notation S sub n. And by the nth partial sum, much as it sounds, this is just the sum of the first n terms. So we can use that S sub n to approximate the sum of the series. So to find the approximate value of S. If we then want to talk about the error in this approximation, we would define this as the difference between the actual sum and our estimate. For notation, I'm going to use E sub n. So importantly, that subscript there is a reference to how many terms we're using in our sum to approximate S. And we're going to define this as S minus S sub n. And if we think about what that equals, well, S would be the sum of all of the terms. S sub n would be the sum of the first n terms. So everything that's in Sn would be in that first collection of terms as well. So by taking the difference, I'm going to leave what's left, and that would be a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3, etc. And I could express that in sigma notation as the sum from k equals n plus 1 to infinity of a sub k. So that now is a formula for the error in using the nth partial sum to approximate the sum. And we can find it in that sigma notation. And I'll also point out that we could have gotten here looking at the sigma notation that we have above for S and Sn. But if we could compute the error exactly, then that's what it would equal. But if I cannot find the exact value of S, I'm not going to be able to find the exact value of this sum, this error term here. So that means, but I will point out that in the instance where I can find the sum, we could compute exactly the error. So let's look at a geometric series. Suppose you were to approximate the sum from k equals 1 to infinity of e to the minus k by its 10th partial sum. So S sub 10. Then the resulting error is, as we've defined it above, e sub 10 would be the sum from 11 to infinity of e to the minus k. However, this is geometric. We could express this as the sum from 11 to infinity of 1 over e to the k. So I can see there that my r value in absolute value is less than 1. Therefore, this converges, and this is going to sum to the first term, which is 1 over e to the 11th, divided by 1 minus 1 over e. So when I can find the exact value of the sum, I'm able to find the exact value of the error in such an approximation. We could likewise look at this for a telescoping sum, because those are ones in which we can also find the sum of the converging series. So in this instance, suppose you approximate the sum of 1 over k minus 1 over k plus 1. That's a converging telescoping sum. We've looked at that previously. Suppose you were to approximate this sum by its 8th partial sum. Well, we can check here. We can show, and in fact we have before, that S sub n is 1 minus 1 over n plus 1. So because of this, the error in our approximation, and I'm referring to approximating that by its 8th partial sum, is e sub 8 equals the infinite sum minus the 8th partial sum. The infinite sum we would find by taking the limit as n approaches infinity of S sub n, and we'd get 1. And we subtract the 8th partial sum, which is, according to our formula, 1 minus 1 over 9. So we would get 1 minus 1 minus 1/9, or 1/9. So in the instance where I can find the actual sum of my series, we can find the exact value of the error. However, typically when we're using this is going to be an instance when I can't find the sum of the series. So our goal is to approximate the sum, and then our hope is that we can provide a bound on the resulting error. It turns out that we're going to be able to do this with some of the tests that we've looked at before. And so I kind of want to take those in turn, look at when we can do this, and then go through some examples in those instances.